Now, we have gone through this before, all right? Alkanes, alkenes, alkynes, and alcohols. We've done all the stuff, preparation, and then properties, preparation, and then reactions of. Let's go over the first one. It's called dehydration. I have a neat little demo for this, but first I'm going to do an equation. What do you think is going to happen in dehydration? Yeah, you're going to remove water. That's exactly what happens, all right? If you add concentrated sulfuric acid to an alcohol, this is what you're going to get. You're going to get an alkane. Let's do an example of that. Say I gave you this guy. And I hope everybody knows who that is. Who is that?
1,2-dimethyl.
No. It's what? Ethanol. It's ethanol. Why should we know him? That's what you made in the lab. Okay. Now, we're going to react. If we react him with sulfuric acid, you will get him. You will turn him into an alkene. You will remove the OH. This is what I like about chemistry, organic chemistry, I should say. What I like about it is it makes sense. Remember, you don't have to draw these all in here, but at the end of every one of these dashes is an H. I'm just leaving them out for simplicity's sake. Now watch. What happens? The OH and an H in the presence of the sulfuric acid are removed, and you get water over here, and what's left over? Well, you got these two guys are taken away, and nothing was added on there, so you're going to be missing two things, and you can account for that by making it a double bond. All right, now there's no balancing required. I got 1, 2, 3, 4 hydrogens here and 4 hydrogens there. 2 of them there are the 2 that were here, and there's the O and there's the O. Everything works out. And that's what's nice about it. Most of the time organic works out like that, and it just makes sense. You also have to name everybody on here. And again, I am going to go fast today because we do have to get through everything. How would I name everybody here? I would name this guy what? Ethanol. Do I have to name water? No. What do I call this guy? Ethene. I don't even need the 1. If you put the 1, I'm not going to call it wrong. But you don't need the 1 here either because there's only one place it could be. If I have anything longer than just 2 of them, if I have 3 of them, I have to number it. If I have an OH, because that could be 2 propanol versus 1 propanol, okay? So I do have to name that guy, all right, with the number in it. All right, good enough. Everybody good with that?
Yeah.
All right. Now I'm going to actually stop this here for a second. Well, before I stop, just say one more thing about it. I'm going to do a dehydration that's a pretty neat demo that you see quite often. It's not technically going to be using an alcohol, but it's going to be using sugar. Look at the formula for sugar. What does sugar have all over him?
OH.
Oops, sorry.
A lot of H's.
Yeah, he's got OHs all over the place. So I can dehydrate the sugar as well. And it's pretty spectacular what happens. Like, it's pretty obvious. So that's why I want to show it to you. Okay, so let me stop the thing here. There you go.
He said it. He said it.
So, look at it. We dehydrated the sugar, which is kind of like dehydration of an alcohol, but it's not exactly the same thing. Sugar's not an alcohol, but it has lots of OHs in it, so it works. Okay, now we've got to go on and get to the next reaction. The first one was dehydration. The next one's reaction with the hydrogen halide, which is basically like hydrochloric acid. If I react an alcohol with hydrochloric acid, for example, what happens there? Again, look at how organic always makes sense. Have ROH plus HX equals RX plus H2O, which is basically HOH. So you all see what happened there? It's a substitution reaction, right? One guy substitutes in for the other guy. All right, let's do in the presence of zinc chloride. And by the way, I noticed something already that was happening with, I think Ali said this, she was doing this in her worksheet. You can't just look at what, a lot of people like to use what the catalyst is and use that as to tell you what the reaction is. It's true, it helps sometimes, but you're going to see the same catalyst in multiple reactions. Delta, she was looking for a triangle. So she ended up getting like crazy answers for some of her things because all she looked at was a triangle. If there was a triangle, she found the reaction that had a triangle under it, and then she finished it. Well, that doesn't work because there's many guys who have triangles underneath them. All right, same thing's true for these guys. You're going to have other guys with acids. You're going to have other guys who have, for example, in a minute, KMNO4. But let's do this guy first. Let's do an example of him. All right, you all have room for one right there, I think. All right, let's do this guy. Oops, I want to use black.
Blank.
All right, take a look at that. Copy that guy down as your first example, as your only example underneath this guy. All right, first off, as you're copying it, let me say a few things. It has to be an OH. I'm sorry, I'm getting ahead of myself. It doesn't have to be anything here. You're good. The OH can be anywhere. But what I want to say is one of the mistakes you made in the worksheets. I just gave those worksheets back to you. Can I put that X anywhere? Where am I going to put them? Where the OH was, exactly. Some people listen too closely to the Markovnikov's rule. Markovnikov's rule says, given a choice, say for example I've got a guy like this, all right? Given a choice, where would the guy want to be added onto? And you would say, okay, he wants to go there because that's the more substituted carbon. But I couldn't very well, if the double bond were here, all right? Now, given a choice, can he go over here? No, but many of you did that in the worksheet. Many of you did, okay? All right, so anyway, let's finish this guy up over here. Do I have to name everybody? Well, no, I don't have to name water. I don't have to name HCl. But I do have to name the organic compounds, so let's name them. And you have to use numbers, because this isn't just meth or F. It's got more than one possibility. What would this guy be? 1 butanol. And that guy over there? 1 chlorobutane. All right. Good. Everybody good with that? So again, dehydration, we remove water, and that is basically remove the OH. You can turn that off now. That's not good. No, it's done. And then over here, you remove the OH to make an alkene. Here, I substitute an X for an OH. Now, what are we going to do next? We have one more alcohol reaction. And by the way, you should keep in mind, as hard as you find that this organic stuff is, it'll be a lot worse in college because I'm only giving you a handful of the reactions that actually exist. There's more reactions than just 3 reactions with alcohols. But these are the 3 I want to use. These are the 3 I want to show you. All right, look at this guy. It's a little weird. We're going to get a new compound, something called an alkoxide. All right? I know, great name.
Wait, what'd you say?
You write that down. I don't think I have that written in there, so write that in there. Oh, it is? Okay.
What is it?
An alkoxide. All right, let's do an example of this guy. Let's start with a very simple one. Let's start with
Alkoxide. Let's do an al. Alkoxide.
all right? Now, the hard part about this one is, again, what happens, you can see from the general formula, and guess what I'm giving you today? I'm giving you the general formula sheet today. So on Monday, when you're working with 2 periods, you won't have to be flipping back and forth through your notes. Every reaction I've given you, including this one, is on this sheet. Now, if you flip me off all you want, I won't be here. All right, what am I going to do? What's going to happen here? You all know what's going to happen even if you can't name it. What's going to happen?
The O and H are
yeah, they're going to switch places, basically. You're going to get rid of the H, and the Na is going to take his place, and you're going to get this. Okay?
That's C dash O dash.
Yeah, there's a bond between it. Okay. Now, everybody knows how to name this guy. What's this guy called over here?
Methanol.
Methanol, right. And we don't have to name sodium, and we don't have to name hydrogen. That's the weird guy. How do I name him? He's called sodium methoxide. Hence the term alkoxide, sodium methoxide. All right? And it doesn't have to be sodium. It could be another strong metal, a very good metal, like potassium, lithium. Okay, look at it. One other thing about this guy, it doesn't happen very often, but even in organic, there's a few that need to be balanced. You notice what happened here? I replaced 1 sodium and 1 H, but because H is diatomic, I got 2 of them over here. So I got balanced with a 2, a 2, and a 2. Okay? And that pretty much covers the alcohol reactions. Yeah.
It's the meth oxide because there's 1 O.
No,
It's meth because there's 1 carbon.
Oh.
If this had been 2 carbons, what would it have been called? Ethoxide. Propoxide, okay? Okay. All right.
Is there ever going to be, I guess not.
Boron.
All right. Now, that was the end of alcohols. This is the beginning of carboxylic acids, and I got to give you the notes on it.
I thought you said you had lots of.
Said what?
You had lots of examples.
I have literally, no, I didn't say that.
Demo.
No, I have a lot of demos. I have a second demo to do, and I'm going to do that in a second. Is he behind you or behind me?
I'm on to it. Let's put it on to
All right, well, we got a brand new compound to talk about, guys, a brand new functional group. Something you're going to see, actually going to see a part of this quite often. This little new thing here, C double bond O. It's called a carbonyl group. And you need to draw that whole thing in, R, C double bond O, OH. Draw that whole thing in there. Because let me tell you something right now. Now's probably a good time as any. Tell you, on the day of the properties, not the day of the reactions, but the other day for the test. We're going to have a test that's not on the reactions, worth about 50 points. I will have a whole section with all of these functional groups on them. And you'll have to tell me what kind of a compound that makes it. So if I have R, OH, I have R, C, double bond O, OH. I have R, C, double bond R. I would ask you, over to the side, by the way, we will have, by the time I'm done, about 12 of these. There's alkenes, alkynes, aldehydes, ketones, esters, ethers, things you don't even know about yet, but you will, okay? So I'm going to list the general formulas over here. And then at the top, I'll have a matching section. All right, so I'll have alkane, alkene, alkyne, the whole 9 yards. What will you put in the blank next to that guy? What kind of a compound is he? Right here. He's an alcohol. If he has an OH and just an OH, he's an alcohol. What would you put next to this guy? A carboxylic acid. You don't know what it is yet. I haven't talked about it yet, but that's what you'll put. What will you put next to this guy with a double bond? An alkene. Okay, so that's a really easy section. If you're doing these, you know what they're called, you should all get like, whatever it is, worth 10 out of 10 on that section. I'll probably have like 2 points apiece, maybe 5 or 6 of these. All right. Okay, now let's get back to carboxylic acids. I'm going to talk about several things in carboxylic acids, and we're going to start with the naming system, the nomenclature. All right, and actually it turns out that most of the ones we're going to talk about do not use their actual UPAC name. They're going to use the common names. And if I buy a bottle of this stuff, it's rare that you buy the bottle, the labels on it says the UPAC name. So that's why you have to get used to these. The 3 I'm going to do as examples, you're going to be in the fume hood next week to do ester lab for. Okay? How do you name these guys? Well, first you do what you always do. You name the alkane and all that that implies. If there's a methyl, an ethyl, a chlorine, a bromine, or whatever the heck is on it, you name it the way you always would. But again, you're going to have to give precedence to this new group we're talking about. I know a lot of you guys are probably wondering, what's going to happen when I have multiple things in the same guy? If I have a double bond and a triple bond and a carboxylic acid and an OH, and they're all there together, who wins then? There is an answer to that. There's actually a chart. I'm going to give it to you. All right, we'll talk about that, but that's not till next unit. I don't want to confuse you now. All right, so you name the alkane and all of that implies. Next, you put, this is a different way to, you don't number it. You don't have to number it, because guess what? That carboxylic acid has to be on the end. Can I put that in the middle of a compound and have another R coming out this way? No, it's not going to happen. H only has a valence of 1. He can be bound to 1 O. He can't be bound out that way. Same thing with this O out that way. I can't have another guy coming off of that carbon. He's already got 4 bonds, 1, 2, 3, 4. So he's always at the end. So I simply add the OIC suffix and then the word acid. So, for example, let's do the easiest one. What would be the smallest acid you could have? I believe I have these numbered like 1, 2, and 3 on your paper, right?
Yes.
So what would this guy be? What would his name be? One carbon long. So what do you call that? Not the alkane. What alkane is 1 carbon long? Methane. So it would be called methanoic acid. Methanoic acid. You have to be careful of whether I say name the alkane or name the alkyl group. If I said name the alkyl group, it would be methyl. If I say name the alkane, it's methane, methanoic acid. Now, none of these, like I said, that we're going to talk about today actually get called by those names. People who want a bottle of methanoic acid ask for a bottle of formic acid. All right? The formic part comes from, I believe, the word We're going to use formic actually for one carbon to mean one carbon in multiple places, formal group, formaldehyde. But the original production of methanoic acid was by destructive distillation of ants.
Huh?
Fire ants. Why? What do fire ants secrete when they bite you?
Acid.
Formic acid, methanoic acid, that's what they secrete. That's why they burn. All right, so if you were to boil a bunch of ants, not uncles, but ants.
Yeah.
If you were to boil a bunch of ants, you would get formic acid because that would boil at a lower temperature than the water would, for example, or anything, or other particles that are in there. And that's how you get formic acid. All right, number two. This guy is even more familiar to you, okay? He is the guy with 2 carbons. And again, you could name this systematically. Now, what would you call him? Ethanoic acid. Right? Everybody would call it ethanoic acid. You may have heard of another name for ethanoic acid is acetic acid. And even if you haven't heard of acetic acid,
I think you've said it.
I know I have, but even if you haven't heard of acetic acid, you've all heard of a 5% solution of acetic acid. You know what it's called?
No.
You put it on your fries.
Vinegar.
Vinegar. Or on your salad dressing.
That's
Yeah.
what I made last year.
Why did they give them the other names? Like, it's not like
I know, and that's it was one of the things, I think in college that was one of the more annoying things is having multiple names for these guys. It's very common to do that, and really there is no reason. You would think by now we would all be, but then again, by now you'd think we'd all be using the metric system, and we're not. When I was a kid, that's what they told the nuns in Catholic school all told me, oh yeah, you got to learn the metric system because someday we're going to all go to the metric system. Well, we still have miles per hour. You know, we still buy 2x4s at the store. We don't use the metric system except for maybe we buy a 2-liter bottle of soda. That's about it. And the same thing's true with this. They just use the common names because they're used to using them. The third one is also another. By the way, the reason I'm giving these 3, I know by now you know how to name these. I think everybody can name these. I'm giving these 3 because you're going to see these 3 and their common names in the fume hood on the lab next Wednesday on the ester lab. All right, there's this guy right here. Now, those of you who pissed me off will get to use this one because this is butyric acid. And butyric acid is one of the most horrendous smelling things in the world.
Really? I think
Butanoic
the
acid.
hallways are pretty bad.
Yeah, it's even worse than Mr. Heck's class. I'm serious.
Oh my
This is-
god. Wow. It's bad.
Wait, how do you spell that?
Methanoic acid, ethanoic acid. What do you think this guy's going to be called? Butanoic acid. Now, the common name is butyric acid. And it comes from butyric butter. It comes from rancid butter in particular, and it causes projectile vomiting. It is an extremely nasty smell. If you were to ingest it, it would cause projectile vomiting.
What's the yeah,
Butyric, that's a B. Butyric acid.
B-U-T.
Y-R-I-C.
Oh my gosh. I thought that was a G.
Oh my God, it's a Y. Look at that. It's a perfect Y. It's an absolutely perfect Y. A G? Butyric acid. You like Russian or something? Butyric acid. A G. A G. I said butyric. How could you think that's a G?
Silent G.
The silent G? When is G pronounced like a Y? Anyway, it's present in butter, in rancid butter in particular, not regular butter, because otherwise you'd throw up every time you ate butter.
Rancid butter, because I think it's regular butter, but it's
This stuff smells like if you took cheese, really, really smelly cheese, and put it in your sock you've been wearing for a week, and then you shove that into a shoe and put it into, a wet, smelly basement for a week and a half, and then took it out and made it somehow smell worse than that. This is worse.
So do you have any of that?
We are going to use that in, and that's why I said people who piss me off, you start being nice to me now, are going to have to use this. Because the nice part about this is once you use it, it kind of sticks with you all day, and people kind of avoid you.
Sorry.
So I should just give it to Bulkley anyway, because that really wouldn't make any difference.
I see you use it a lot.
That's right. Okay. Now, so that's the naming system. Good with that. Next is properties. Yes. And these are the things that are going to show up on the other tests, not the reaction test. Now, the properties, up till now, I've been concentrating property-wise on several things. Listen, I'm concentrating on boiling point and melting point, boiling point and melting point. I've been concentrating on solubility in water or not. And we talked about branching and OH groups and hydrogen bonding and stuff that would affect that. We have one more thing we're going to talk about today. What's that going to be, you think, since this is carboxylic acids? Yeah, whether it's an acid or a base. Do you remember what makes something an acid or a base?
Color, litmus color.
Well, no, that doesn't make it that.
Oh,
All right, so acids generally tend to have H's, and bases generally tend to have OH's. Why? What exactly is it that an acid does with that H? What does it do with it? Like let's look at, don't draw this, but let's look at hydrochloric acid. Hydrochloric acid reacts with water. Do you remember what happens when that happens?
H3O.
Yeah, you get H3O, exactly, because this H adds on to that guy, and then you're left with chloride. This basically illustrates both the Bronsted and the Arrhenius definition of acid. Bronsted, remember, you don't have to know this. I'm not going to ask this on the test, the difference between these. But remember, Bronsted said an acid is anybody who gives up an H. Arrhenius said an acid is anything that forms these guys. What are they called? Not hydroxides. The opposite, pretty much. Remember? Hydronium ions. Hydronium ions. All right, so what do you have to know about acids, about carboxylic acids? That, no surprise, they are weak acids. Get that weak acid out. Weak acids, they donate hydrogen ions, that is, they donate protons, and they form hydronium ions in solution.
I really just spelled weak with C.
That's weak.
That's weak. That's just weak. All right. So that's another thing we're going to talk about a little bit, because there's going to be an organic compound in a little while we're going to get that's going to be basic. We'll talk about those guys, amines.
He didn't do great on the standardized testing of basic.
It was basic. Yeah, you guys got basic. All right. Another thing about alcohols, carboxylic acids, back to some of the stuff we've been talking about, solubility. You would expect this carboxyl group. Now, I want you to look at this, because I abbreviated to fit it on one line. I needed more room. Molecular weight, that's what it says. The low molecular weight acids, that is the smaller ones, the ones with fewer carbons in it, will tend to be soluble in water because they've got that OH there again. And that OH is polar. And, like dissolves like. That's the only real rule of solubility you need to know. So if I've got some OHs in there, the more carboxyl groups I have and the less carbons I have, the more soluble it's going to be in water. I'm going to give you a couple of examples in the test. Different compounds, I'll ask you which one would you expect to be more soluble, which one would you expect to have a higher boiling point. Now I could add which one would you expect to be acidic or basic. We haven't really, the other guys haven't talked about acidic or basic, so it would probably be either this guy, the carboxylic acid, or an amine, which I'll talk about in a couple of days or in a week or so. All right, good enough on the properties. Now let's get to the reactions, preparation reactions. We don't have a whole lot of time. We've got to get through this and another demo. The demo's pretty cool. All right. Oxidation of a primary alcohol. That's what I'm going to do here for my demo. Okay? We're going to oxidize a primary alcohol. This time, as I almost said it a little while ago, has to be a primary alcohol. What do I mean by primary alcohol? We'll take a few seconds because I know you've forgotten. What do I mean by primary alcohol? Let's say I've got this compound and the OH is here. Is that a primary alcohol? What did I mean by primary, secondary, and tertiary? Remember that from like last week? It meant this guy's attached to a carbon that is attached to only one other carbon, right? Yeah. So that is a primary alcohol. What if the OH were on this guy? What would he be then? Secondary. What if you were on this one up here? Tertiary. No, he would not be tertiary. He would be primary, because this carbon's only bound to one other carbon. If he were bound to this one, he would be tertiary. And if he were bound to this one, he would be primary. You see, because this carbon's only bound to one other carbon. He's got H's around. This carbon, HH, OH, and then one other carbon. But this carbon's bound to 1, 2, 3 other carbons. Okay. Now, having said that, it has to be a primary alcohol for this to work, because that carboxyl group has to go on the end of the carbon chain. So let's do that. General formula looks like this. I'm going to do this reaction in a minute, in the fume hood.
Wait, what's the NVR?
I will tell you about that when I get to it in a second. When we get to the end of the reaction.
I thought it was part of the reaction.
No. That what you have written down over to the side, NVR. I will talk about that in a few seconds. Okay? But let's do an example first. And the example I want to do for this guy, what are my notes, is
Bronsted reaction.
this one.
Non-Broadstead reaction.
I don't know what that means, but
I
okay.
don't know what the hell it is either. Unless you just told me to yell.
No.
Why?
That's it. You're getting the...
I'm getting that answer. I want
All right.
that answer.
Now, if I give you that reaction on the test, you would be able to finish it, I bet you. And I think now, at this point, you could actually name everything on it, too. But there are little mistakes you'll make. Let's first of all worry about finishing the equation. How's that going to look when I finish it? One of the mistakes I saw, again, even though I warned you about it, people who do this. They concentrate so hard on getting this part right that they completely forget about something else. If you look at your worksheet, you'll see that they forgot the methyl group up there. It was there. You don't just delete it. So that's one thing you could do wrong. All right, but obviously you're making the carboxylic acid where the OH was. You don't have a choice of where to put that. You put it where the OH was. Secondly, we got to name everybody, and this is the mistake people make. I do not name this guy 2-methyl. Why? OH takes precedence. It's got to start from this side. 1, 2, 3, 4-methyl.
Precedence.
4-methyl what?
No.
Butanol.
Ah, again you're forgetting something. 1-pentanol. Now this guy over here would be?
Whatever you want.
What would that guy be? Still 4-methyl what? 4-methyl pentanoic acid. In this case, I do not need to write the 1 in front of it. Okay? I mean, I probably wouldn't take off for it, but you don't need it because a carboxylic acid group has to be on the end. Okay? So it's just pentanoic acid. 4-methyl pentanoic acid. Okay? Everybody got that one? Now I'm going to do another demo of this here, but I'm not going to use 4-methyl pentanol to do it. I'm going to use something that gives you a really cool reaction again. But it still illustrates the point. Watch. I'm going to use this stuff here. Glycerol. Notice glycerol, again, like the last time I used sugar, glycerol has lots of OHs. And glycerol is just glycerin, stuff that you would use to lubricate a needle, stuff you would use in soap. You hear of glycerin soap? Okay. This is glycerin. It's like a lubricant. All right. Now I'm going to use this with some potassium permanganate. It's a pretty cool reaction. Something about that MBR is next to that. You'll notice something. When I did the equation, it wasn't balanced.
No balance.
And no balancing required. Okay. I'm not going to ask you to balance this. I'm not writing out the entire equation of what happens with the KMNO4, but basically that's providing the oxygen, the extra oxygen you need onto here. So you don't have to worry about balancing this and a couple of other ones throughout the rest of this year, this chapter. I've already said most organic reactions don't need to be balanced. This is an example of one that we're not going to worry about balancing. The oxidation reagent, the KMNO4, does provide that extra oxygen, but I'm not going to include him in the equation. Okay. All right, let's get to the next type because we're almost out of time here. What do we got here? Reactions of potassium permanganate, reduction into an alcohol. I can take this guy and turn him back into an alcohol. This is the same thing we just saw in reverse, isn't it? It's the same thing we saw in reverse. And once again, I don't want you to worry about balancing this guy. I don't even have room for an example underneath him, do I?
Nope.
No. All right, but you all see what happened here. Here you take a lithium aluminum hydride, and he basically will get rid of that oxygen. He's a reducing agent, what we call a reducing agent. Okay? The next one, unfortunately, you're going to have to wait till Tuesday to see. Conversion into esters, and the example I'm going to do below that, we're going to do on Tuesday. Right now, I need to give you the worksheets